So 17.4, in any case, I think I can still give the lecture, even if I'm asleep. We're going to be talking about Green's theorem, which is, you can think of it as the first of the great theorems of vector calculus. Okay? What we'll see are, if you go on in mathematics, you'll find out that all the great theorems of vector calculus are just the same, all the same thing. They're all actually one theorem. But at this point, they're going to seem like three different things. Okay. So here it is. You have a C, a positively oriented, and I'll explain that in a second, positively oriented, piecewise smooth, simple closed curve. And I'll explain all these terms in a second. In R2. And you let D be the region bounded by C. In other words, C is really the boundary of D. This notation means boundary of D. Okay. If P and Q are going from R2 to R, are functions on an open region containing D, and have continuous partials, then the following is true. Then the integral around the boundary, right, around C, the integral around C of Pxy dx plus Qxy dy equals the double integral of dq dx minus dp dy against area over the interior. Okay, so let me explain some terms first. C, a positively oriented, piecewise smooth, you know, right? It's in pieces, each of those pieces is a smooth curve. Simple means that it doesn't cross itself, okay? Doesn't cross itself. Okay. Closed means that, you know, it's a loop, the beginning and the end point and the initial point are the same, right? The only thing that's a little bit tricky is positively oriented. Okay, so you have this thing, right? It's basically a loop. Ends and begins at the same point. Positively oriented is used to describe in what direction you go around the curve. And it's this, that if you are walking on the curve, then the inside of the curve is on your left. Okay, that's what positively oriented means. If you're standing here on the board and you're walking, then the inside of the curve is on your left. So that's what positively oriented means. And one often puts a circle here with an arrow going this way to indicate that you're going around this positively oriented curve.
Then how come it wouldn't work in the other direction if it's just the same path, like backwards?
Well, then you get negative this,
No.
right? So you get
Does it
you
just
just have to adjust the formula for it.
Does it just choose what positively oriented means just arbitrarily? Just that it's counterclockwise?
Yeah. It's you could say that it's entirely arbitrary. We could have chosen positively oriented to be the other direction. You know, like if they had chosen at the beginning to be positively oriented the other way, then all the formulas would have just have negative signs on them. Yeah, so you're right, it's arbitrary. Okay, so what this is saying is that if you take this line integral, right? You're taking this line integral of this thing against dx and dy, and maybe at this point I should say that it's maybe easier for you to think of this thing as if we let f of xy be the vector field pq, then that left-hand side there, this thing p dx plus q dy over c is the same thing as f dot dr over c. Right. So it's actually the integral. What we're really looking at is the integral of a vector field around a closed curve. So, and this thing is called the circulation of f around the curve C. Okay, so what this theorem is saying, what Green's theorem is saying, is that the circulation of a vector field around a closed curve can actually be calculated as the double integral of some function, the double integral of some function on the region enclosed by that curve. Okay. Okay. Again, does this remind you of anything? Is this reminiscent of anything? Fundamental theorem of calculus, yeah. Fundamental theorem of calculus, right? The fundamental theorem of calculus, one of them at least, says that to integrate, if you're integrating from a to b some function, right? You're integrating over the interior here. All you need to do is take the antiderivative and evaluate that on the endpoints. Right? Evaluate that thing on the endpoints, and this is sort of the same thing, right? Well, if you're trying to integrate this function, on this region. In fact, all you need to do is evaluate the circulation of this field around the boundary. Okay, so yeah, that's right. So you can think of these things. These endpoints are the boundary of your interval. Right, they're the bounds of your interval, right? So this is evaluating this thing on the bounds, right? You can either evaluate this thing on the bounds, or you can integrate the whole thing on the interior, right? You can either evaluate this thing on the boundary, or you can evaluate that thing on the interior, right? So that's the analogy, and this analogy will keep on going. Okay. Any questions about the statement? Questions about the statement? Okay, so let's do some examples before we explain how this works. Okay, so for example, if we consider the integral negative y dx plus x dy over some boundary, right? This is, our field is negative yx, right? So what Green's theorem says is that if we take dq dx and subtract off dp dy and integrate that thing over the area, right, over the interior, right, then we'll get the same value. Right? So taking this line integral is the same thing as taking this area integral here. But you notice what this area, look at what this area integral is. What is this? What does this give you? If you integrate 2 times 1/2, well, that's just going to be the integral of 1. Right? The integral of 1 over this region. What is that? Yeah, the volume. In this case, it'll be the area, right? The area of P. The area of P. Flo, your hands are green.
No, I just tied up.
Oh, I see. When I was a graduate student in Chicago, I heard that the previous year, one of the students had come in having dyed his whole body green. And soon after that, he dropped out of the program. Yeah, that's not the full story. Okay, in any case, so this is pretty good, right? Right? It says that if you have something like this, and you're wondering, what is the area of that object, then you could get it by taking a line integral, around the boundary, like this, and that would do it. Okay. In fact, and this is the toy that I was hoping to bring in, that I forgot to bring in. They did this. Engineers made a toy that would do this. In the late 19th century. Probably after Green's theorem was figured out, they made a tool for architects, which you just put it on the edge of your thing and you run it around like this, and it's this thing with gears, and then you get to the end again and you read off. It basically calculates a line, the appropriate line integral as you're going around, and then it tells you what the area is inside the thing you've traced. Yeah, I was going to bring one in, but it's in my office. If you're curious about it. Okay. Yeah. Oh yeah. Okay. I forgot what it's called, but I wrote in my notes. It's called a planimeter. Planimeter, and you can buy them on eBay if you like to. I got mine for $36, but like an old planimeter, from the beginning of planimeters, it may run like $100 or $200. Okay. Yeah. Okay. So that's example 1. Example 2. This is part of example 1, but we'll call it example 2. Let R of t be a cosine t, b sine t, as t goes around the full circle. Okay. So this is right. This is an ellipse. This thing is describing an ellipse, right? Where a and b are positive numbers, right? A gives you the length of the major axis of one of the axes, and b gives you the length of the other axis, right? Right. And so if we wanted to calculate the area of this guy, well, we just say, okay, we're going to do then the area of this ellipse is, you just calculate it. Right? It's going to be 1/2 the integral from 0 to 2 pi of negative y dx. Right? So a negative sine plus x dy. So that's b cosine t dt. Right. So that gives us you can calculate the area of an ellipse in this easy way using Green's theorem. Oh yeah, Lily.
Why do you take the 1/2 there?
The 1/2, because if I didn't have this 1/2, then what would my integral be equal to?
2.
Twice the area.
Okay.
Yeah, that's the only reason. If you want, I can put the 1/2 inside. It doesn't matter, right? but you see how it goes, right? If I don't have that 1/2 there, then I'm going to get the integral of 2 over the area. I'm going to get twice the area. So I just throw it in to fix that. Okay. Okay. Here's another example. The integral over c of y plus e to the square root of x dx plus 2x plus cosine y squared dy. And it'll look bad, but you know that this is set up to make Green's theorem look good. So things will, everything's going to simplify. Okay, and somebody says, I would like you to integrate that guy over c, and c is going to be what you get when you take one parabola and another parabola. Okay, so y equals x squared and x equals y squared, and I'd like you to run that thing over, it. So over this curve here. Okay. So right. So if you want to do this directly as a line integral, right? So as a line integral, think of what you would need to do, right? As a line integral, you need to make a parameterization of the curve, right? So you could parameterize C as, say, R1 t goes from is t comma t squared, right? So that's going to be I'm going to do it in 2 parts, say. So t comma t squared goes from 0 to 1 along the bottom line, right? So this guy's going to be R1 here. Right. And then R2, I'm going to do as t squared t. Again, t goes from 0 to 1. That's actually in the wrong direction. Right, that goes from 0 to 1 along the top line. That goes from 0 to 1 along the top line, but I'll just subtract, right? And I'll just subtract one from the. I'll just subtract the second guy to get it going in the right direction. Right. Okay. So then you parameterize this guy, and then you would, evaluate your line integral, right? So and evaluate. Right. So that would be one way to do it, and it would be pretty awful. Of course, it'd be awful because we've chosen this example to show how great Green's theorem is. Okay. So instead, that's one way. Could do as a line integral, okay. Or you could use Green's theorem. Say, okay, well, this is going to be the integral over the interior dA of dq dx, right? dq dx, of course, is just 2, right? Minus dp dy, which is 1. Right? Right, so again, you get this area thing, and then you just calculate the area.
Would both of the integrals be going from 0 to 1 still?
So we're not in this case. We're not going to use a. We're not doing a path integral anymore. We're not doing a line integral anymore. We're just doing an area. Right? So what we get is the integral of dA over this region D. Right? This region D is this thing, and then you would express this thing as a x simple or y simple region, and then you just calculate what the area is. Using just using what we did before in previous chapters. So we're not going to do it as a line integral. Right? This is a double integral,
Mhm.
and you just evaluate your double integral.
Okay. I was just.
What's your
wondering,
question?
From where to where? Like, what are the boundaries of the integral? Integrating from.
Yeah. So what is it? Right. Right. This guy on the bottom is x equals y squared. Right. This guy on the top is y equals x squared. Right. So you could say, right, how do you want to take it? Do you want it to be x simple or y simple?
X.
X simple, of course. 0 to 1, right? So dx, right? dy, right? X equals 0 to 1, and for fixed x, what's the y going to be? Square root of x up to
X squared.
x squared. Okay. Alana and Flo, did you have questions or have answers?
That was the same question.
Okay. Sydney.
Wait, aren't the lines the reverse?
Yeah.
Did I mess
Square root
up?
of x on top.
Oh, I'm
X
sorry.
right on the
Yeah.
top.
Sorry. Thank you. Thanks. Okay. Okay. So yeah. So Green's theorem is pretty nice. Oh yeah. Okay. Let's do another very important example. Notice that the area, right? The area we see could have been calculated as the line integral of two different things, right? Two different things. We had one line integral here that gave us the area. We have a completely different line integral there that gives us the same area, right? This is basically the notion of antiderivative, right? If you have the fundamental theorem of calculus, right, you can evaluate any antiderivative at the endpoints, and you get the same number, right? Both of these things are basically like antiderivatives of the thing that gives you area. Okay, right? It's that is you shouldn't be surprised that that you can have two line integrals that give you the same thing, right? You can evaluate. Right. You could evaluate this guy on the boundary, or you could evaluate that guy on the boundary, just as you can evaluate different antiderivatives on the boundary, and it won't change the value. Okay. The next is an important example. Because it will foreshadow something that happens later on. Okay. So let's see. So let me give myself some more space. So xy, let that be 1 over x squared plus y squared negative y comma x. Okay. And maybe it's cleaner if I write it all together. Sorry. Negative y over x squared plus y squared, comma x over x squared plus y squared. Okay. Now, let's suppose we take, let's say that this is the origin, and we have a circle. Okay. We have a circle here, and we have another loop. Okay. Going like this. Okay. And let's call this guy on the outside C and the guy on the inside C prime. And they both have the same orientation. Okay. So now Green's theorem says that if we traverse the boundary in a positive way, right? If we go, let's call this thing D, as we did before. So D. Green's theorem says that if we integrate this field over the boundary in a positive way, then we're going to get the double integral of dq dx minus dp dy dA on the interior. Okay. And here's one thing to pay attention to. When we talk about going on this boundary positively, well, that means that when we're walking on it, we have the interior on your left-hand side, right? So this thing here is going to be the integral over C of f dot dr plus the negative the integral of C prime, because we want to have the interior on our left-hand side, right? And right now, if we walk around it, on our left-hand side is not the interior, right? So here we're going to say C prime, but minus that. Okay. Just to clarify what we mean by the positive orientation. It's not always counterclockwise. Right? It means when you're walking, the interior is on your left. Okay. Okay. So what we have right now is that f dot dr over C plus f minus f dot dr over C prime. Maybe I'll write it like this. The integral over C and the integral over negative C going the opposite directions. Okay. And then here I'll just move the minus sign up because we're allowed to. Equals the double integral of dq dx minus dp dy. Okay. Now, if you calculate dq dx, you get y squared minus x squared over x squared plus y squared minus y squared minus x squared, and then dp dy gives you this thing. But you see that what that is, that's 0. Okay. That turns out to be 0. And so what that tells you is that the integral of f over C equals the integral of f over C prime. Right? I could take I could take the integral, right, the integral over c is the same thing as the integral over c prime. Okay, so so you could take your c to be as wild as you want. This is sort of interesting, right? That you could take your c to be anything, right? If somebody says, what is the integral, right? What is the integral of this field over this curve, right? They say, what's the integral of the field over this curve? You say, I'm not afraid. You know, for this field, I know that the integral over this thing, it's okay to deform the curve down to the circle, and I'm going to get the same answer. Okay, and so all you need to do is calculate the integral of the thing over the circle. If you do calculate the integral over the circle, so just calculation, right? If we let r of t be cosine t sine t, as t ranges from 0 to 2 pi, and actually do the calculation, right? So f dot dr, we end up with, of course, negative y, negative sine t, comma cosine t, dot r prime, negative sine t, cosine t, dt, as t goes from 0 to 2 pi, and so that's 2 pi. Right, because the x squared plus y squared turns into 1 on the unit circle. Okay, so there's something peculiar. There's something unusual about this field, and it won't be obvious to you yet, but it will soon be. We'll soon figure out what that quality is that allows us to deform the path of integration. Okay. Any questions about that? Any questions about that? Yeah.
Back there, how did you get the bottom to be squared? X squared plus y squared squared?
So let's see. So this one is going to be we get dq dx, right? So right now we have x squared plus y squared, right? And you differentiate that with respect to x, right? So you get the bottom times the derivative of the top minus the top times the derivative of the bottom, right? Over the bottom squared, right? By the quotient rule, right? And so you get x squared minus 2x squared, so minus x squared plus y squared over x squared plus y squared. Yeah, so that's the statement.
But I thought you differentiate the first one with respect to x and the second one with respect to y.
You differentiate this one with respect to x, and then subtract this one's derivative with respect to y.
Oh, yeah.
Right, so it's dq dx minus dp dy.
Okay.
Okay. There should be something that bothers you a little bit about this. What if I take a smaller circle and a smaller circle and a smaller circle and a smaller circle and a smaller circle? Right? And make them smaller and smaller and smaller and smaller and smaller. Or let me ask like this: why could I take this circle? Would this be okay to take this circle? Could I shift it to any circle? Is the integral over any curve the integral over any curve? Could I use Green's theorem, right? Could I use Green's theorem on like just any pair of circles like this? Right, so I've got one guy that goes like this, and I've got one guy that goes like this. there's trouble with trying to use, so that actually I can't use Green's theorem in this case. And the reason is that if I look at my field blows up at the origin. Okay, right, at 0, right, my field goes crazy. Right, it's not, and for Green's theorem, we needed our field to have continuous partials throughout, right? So if I have these two, then I'm integrating over D, and on D I'm fine, right? My field is good, right? But if I tried to do something like this, then that would be no good, because then my field goes crazy at this point, and I can't use Green's theorem anymore. So there's some limits to what you can do. So this is a foreshadowing of something that we'll call deformation later on. Okay, so let's give a sketch of Green's theorem. Not the whole thing, but just a bit of it. In the case that D is doubly simple. Okay, so suppose you have this function, suppose you have this guy D, and D is x simple, so you can express it as an x simple region. And you can also express D as a y-simple region. Okay. So we're only going to do part of it. So here's the part we're going to show, that the integral of p dx dv over the boundary equals the double integral of the negative delta p dy dA. Right. And then the other part will be to show that, you know, the integral of q dy equals the integral of dq dx dA. Okay. So the proof is not all that exciting. You just do a calculation. So you say, okay, well, look, let's parameterize, right, our region. We can parameterize the boundary as, so we've got gamma here and delta up here. Okay. So we're going to parameterize it as C1 being T gamma of T, as T goes between A and B. And C2 is going to be T delta T, as T goes from A to B also. Right? There are, you know, you've got this thing, and it's got sort of obvious parameterizations. Okay. Right. Okay. So then the integral of p dx over the positively oriented boundary of B is going to be the integral of that thing over C1, right? C1 is the lower guy, and then minus the integral over C2, the upper guy. Because C2 is going the wrong way, so we subtract it. So, and then we just calculate it, right? we just calculate it, right? It's going to be the integral from a to b of p evaluated at t comma delta t dt minus the same integral over p comma delta t dt. So you go over the gamma part first, and then you subtract off the guy going over the delta part. So that's, let me hold that for right there. And now let's look at the other thing. Right? So negative dp dy dA. So that, if you think about that, that's going to be negative dp dy dy dx. As x goes from a to b, and y goes from gamma x to delta x. But you see what that's going to be. That's going to be the integral from a to b of negative p x delta x minus p x comma gamma x dx. Because you're integrating with respect to y the derivative of p with respect to y, right? And so you anti-differentiate that, and you evaluate it. Right? You get p evaluated from y as from y equals delta x to y equals gamma x, right? And so just by calculus, one variable calculus in the second variable, you end up with this, and you see that those things are equal. Okay. So at least in this one case, the proof of Green's theorem is pretty straightforward, and I think the higher cases involve taking your thing and then chopping it up into things that are doubly simple, right? So that's actually not so easy to show. That you can take the things that we've described, and you can always make them into regions of some combination of regions that are all doubly simple. In any case, this